Okay, so today we are going to continue talking about modules and specifically conditions on finitely generated modules. When a module is finitely generated, um, when it's placed in a short exact sequence. So we are going to let n be a submodule of m, and we want to prove that if both m mod n and n are finitely generated, then so is m. This is a pretty standard result, and the way that we're going to go about it is by looking at a short exact sequence. So we'll start, let n be a submodule of m, then we can create this sequence here. So we have 0 mapping into n, we have the canonical inclusion mapping, iota, that's the symbol that we've denoted that, of n into m, and we have the canonical projection of m onto its quotient of m mod n, and then we have the 0 morphism. So this is a short exact sequence, and now to see why it's exact at each step, we can see that it's exact at m because, of course, the image of iota is n, and the kernel of pi, which is the canonical projection, is also n by its construction. By modding out by taking m and modding out by n, we are essentially setting all the elements of n equal to 0. So naturally, the submodule n will be exactly the kernel of pi. So that means that we are exact at m. Now, being exact at n, this is pretty simple to see. The inclusion map, that's an injection, and the kernel of this injection is going to be trivial. And we see that, of course, the injection of 0 into n is also an injection, as I said. So we're exact at n because the image of the injection of 0 into n is equal to the kernel of iota, which is just 0. And for similar reasoning, we see that we're exact at m mod n. The projection of m mod n onto um, onto 0, that's the kernel of that map, of course, is the whole module m mod n, and the canonical projection is surjective by construction. So we are exact there. So this is a short exact sequence. And this is important because um, when we want to prove, we're going to prove the general case here. So we're going to prove the case that if we have any short exact sequence, so we have 0 mapping into p, p mapping into m through phi, m mapping onto r through phi prime, and then r mapping onto 0. So we have a short exact sequence. When both p and r are finally generated as r, pretty bad notation, let's say as k modules, then m is finally generated as a k module as well. So we're going to prove this general case, and that's going to easily apply to the short exact sequence that we saw in the beginning. So since P is finally generated and R is finally generated as K modules, we're going to let A1 through AN be a generating set of P, and B1 through BM be a generating set for R. By exactness at R, phi prime is surjective, so there exists C1 through CM in M such that phi prime of C sub j is equal to B sub j for all j from 1 to m. So essentially all we're saying here is that since we are exact here, that forces this guy right over here, phi prime, it forces that guy to be a surjective morphism. And because of that, our generating set for R has pre-images in M. So that's all we're saying there. Now, our claim is going to be that phi of A1 through phi of AN and C1, C sub 1, so our pre-images, the pre-images of our generating set for R and the images of our generating set for P, these are going to be, these combined are going to be a generating set for M. Okay, so essentially what we're saying is that we have a generating set for R, and we're going to look at their preimages in M, and we have a generating set for P. We're going to look at the images of that generating set in M. The combination of these two sets is again going to be finite because it's a union of a finite union of finite sets. So of course it's going to be finite, and we claim that that's going to generate M. Okay, so now we're going to let K be an arbitrary element of M. Then if we map K into R, we could write phi prime of K as some linear combination of the basis elements for R. Now we could also write, so we have this expression here, and we can write this expression again, but we could rewrite it because we know the preimages of our b sub 1 through b sub m, those are going to be, the preimages of those guys is going to be phi prime of c sub 1 through phi prime of c sub m. And we could pull out the phi prime because of it's an R modular homomorphism. So we have so we could consider the element, right? So we have two expressions here. We have our element K, and we have our image of K, which we can write in this form. And we're going to look at, right? So we have our element K, and we have the image of K, which is written in this form, R1 C1 plus dot 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 RM CM. So now we're going to consider the element K minus R1C1 plus dot 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 RMCM. So now this, of course, this is an element of M. And if we apply phi prime to that, we get phi prime of K minus phi prime of this linear sum here. And we know that phi prime of this linear sum by our previous work is just phi prime of K. So we just get phi prime of K minus phi prime of K, which is going to be equal to 0. So this implies that K minus R1C1 plus dot 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 through RMCM, that's in the kernel of phi prime. Now, this is important because since we're exact at M, the kernel of phi prime is exactly equal to the image of phi. So there exists some P in P such that phi of P is equal to this element that we started off with over here. That's what exactness guarantees us. But we know that in P, every element can be written as a sum of the generating set. So we have P is equal to T sub 1 A1 plus dot 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 plus T sub n A sub n for some elements of our, from some T sub I in our ring. So we have this relation, phi of P is equal to K minus R1C1 plus dot 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 RMCM through our exactness condition at M. So this implies that K is equal to this sum, phi of P plus our linear combination of the pre-images of basis elements in M. The pre-images of basis elements of R in M. Those pre-images are in M. So now we could expand this out. We have K is equal to phi of P plus, like we wrote before on the previous slide, R1C1 plus dot 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 RMCM. But that's the same as phi of T sub 1 A1 plus dot 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 T sub n Cn plus the same summand down here. And then we could just pull our phi through the sum, and we get a sum of elements. We get a sum of elements of the images of generators plus the sum of pre-images of generators, which exactly shows that we can write this element K as an R linear combination of the elements phi of A1 to phi of AN and C1 through CM. So now we have shown that M is finitely generated. And now if we apply these back to our original conditions, we see that if N and M mod N are finitely generated, then so is M.